Thank you so much, Raj. And thank you again, Secretary Grahn, for sharing your thoughts with us. We are really happy to hear all of the conversation around mobility that we've had so far this morning. And we thought we'd take this period of time to be able to look at the research that is happening through the University Transportation Center. And one of the things we are trying, which is a little bit different this year, is that we have videos that have been put together. And so during the time that the videos are playing, we would like you to think about how these projects may relate to you, how information you have might be helpful to the researchers to know, and any other questions you may have about the projects. So we're going to go to the next slide. We will get started. And our first project that we're going to be hearing about is led by Alexander Hauptmann. And Lijun is going to be telling us about vehicle trajectory and gap estimation for conflict prediction.
Hello, this is Vehicle Trajectory and Gap Estimation for Conflict Prediction project, led by PI Xander G. Hauptmann, presented by Lijun from CMU Language Technologies Institute. In this project, we propose Argus traffic activity detection system. It supports real-time activity detection for vehicles and pedestrians, which enables immediate emergency alerting and identification of high-risk areas for traffic planning. It has achieved state-of-the-art performance on extensive benchmarks at NIST Active, TrackWeight, CVPR, and SECV. The figure on the right shows the overall architecture of Argus, which starts by object detection and tracking to generate activity proposals and filter them based on foreground segmentation. Activity recognition labels these proposals, followed by deduplication process to output the final instances. This will be covered in the following video. For each camera, Argus system does object detection, tracking, background subtraction, proposal generation, and activity recognition. Object detection locates object types of interest in each image, and the tracking associates them across frames. Background subtraction removes stable objects such as parked cars. Then for each identified moving object, we will generate activity proposals, which is spatial temporal region of interest. We leverage a format of dense overlapping spatial temporal cubes as our proposals. Here we can see the proposals are oversampled in the temporal axis to ensure coverage of activities and completeness of detection. Finally, activity recognition labels these proposals with the types of activities occurring. The system supports multiple labels. Here we can see that person entering vehicle opens the door and unloads the vehicle. Across cameras, Argus also supports 3D object detection, geolocalization, and so on. The 3D object detection locates the 3D location from a single camera, where geolocalization leverages drone or satellite views to project the ground location into the bird's eye view. Multi-view tracking allows multiple cameras to be used to track a single object to ensure the view of angles. And activity localization also projects the detected activities with the relative location of participants into the bird's eye view. That's all. Thank you.
Okay, thank you very much. So, Lijun, I see we have a question already from Stan. Stan, you want to unmute yourself and ask your question?
Hi, thank you very much. To the the video where the vehicles and the pedestrians were interacting around the intersection, what's the application that you're looking for in this gap analysis of how this would, inform transportation engineers or planners?
Thank you, Stan. Well, actually, there are a series of applications that this research has potential for. For example, we can detect vehicle turning and going straight activities for traffic planning at intersections, like scheduling of the traffic lights. And more importantly, we would like to detect close interaction between vehicles and pedestrians, such as almost collision events. That is for safety precautions that we need to change the road planning in this situation to prevent their going too near each other.
Yeah, if you can identify the industry terms near misses, that's very valuable to transportation planners. So thank you very much. Great research.
You're welcome.
Okay, I'm curious what the next steps you see in the research project.
Yeah, there are several aspects. First is continuously improving the accuracy in this detection algorithm. So far, we have leveraged from a completely unusable system to as we can see in somehow accurate detections. But if we want to use it in some critical aspects, such as we also applies it to autonomous driving vehicles, we want it to be more specific and accurate about activities detected, like a moving vehicle in front of us. And further, for current research is mainly focused on a stable camera, like a surveillance view. But for traffic, we may also want to leverage the moving cameras installed on a vehicle, maybe a surveillance camera above the vehicle, or just a driving assisted camera in front of them. And also the multi-camera aligning algorithms has great potential. If we can leverage like a city-scale multi-camera network, and we can calculate all of them and tracking vehicles across the whole city, and see if a potential subset of the vehicles that can occur high-risk events more than the others.
Thank you. I appreciate you staying on and answering a couple questions. We are going to move on to our next poster session.
Hello, this is
And this one is from Pingbo Tang and Chenyu Yuan. And they're going to be talking about toward data-driven and continuous safety inspection of commercial trucks and trailers. Again, feel free to drop your questions into chat or raise your hand in the Zoom function and we will call on you. Thank you.
Hi, everyone. My name is Chen Yuan, and I'm a PhD student from Civil and Environmental Engineering Department. And my advisor is Professor Pingbo Tang. He's also from the same department. And the topic of my research is towards data-driven and continuous safety inspection of commercial trucks and trailers. So I will introduce our project vision first. So the purpose of our project is to predict fleet performance and proactive fleet maintenance based on government criteria. So we have 7 different kinds of categories to show the rating system of carriers. And we also have a lot of challenges currently towards operators and fleet managers. So I listed all of them here. So based on this kind of criteria and challenges, we need to use our historical data related to inspection and crash and some real-time data related to telematic systems to predict which part of the categories will have a high risk for the operators and fleet managers. So we can set up a data collection plan for our companies to give some better feedbacks and suggestions to the carriers. So the overall goal of our project can split into two parts. So the first one is to build a data analytics architecture to hold tractors and trailers inspection and crash data. So we will fully understand all the data sources and compare the differences. And we will also compare the failure rates of some key criteria like the tails, brakes, and lights at different kinds of intervals, dimension, and types of inspections. And we will finally establish some sort of online dashboards to display all the results. And another task, we will tie real-time data to the database connecting sensory information by use of telematics. So we all know that time is money, so we will justify that the automatic inspection results is better than the manual inspection results. And we will determine which part of the components will be inspected automatically. And we will also develop some overall predict analytics model so we can ensure that the operators could see the expected results of the components degradation and sensor failure. And finally, we will cooperate with our partners. So we will check whether their platform is able to achieve some or all of these expected performance improvements. And we will determine, can we do better for this kind of platforms? So we will improve that part, so give better feedbacks and suggestions to our carrier and operators. And thanks for listening. This is the end of my presentation today.
Okay, thank you very much. Do we have any questions? Because I have one. When you were working on this project, what was the favorite part of your research that you got to work on?
Thanks, Lisa K. And I think the favorite part of my research is to do some machine learning or data to establish some machine learning model and do some data analysis to find that which one is the most crucial part or the most crucial component for our safety inspection. So we can know that this component is very crucial and it will make an influence on our road safety. And in this way, we can install some devices like the telematics sensor to this component to monitor the condition of the component. So we can give some instruction to the fleet manager or to the driver to periodically check the health of this component. So I think I'm working on such kind of data analysis to figure it out. So that's my favorite part about my research.
And so one other follow-up question is, what got you interested in this topic? Why is this what you wanted to work on?
Yeah, I think road safety is a very big problem for the current world, and there's a lot of crash happening on the highway, and it's very consuming to do a lot of inspection for each trunk. And because we are doing a lot of inspection each year, like the periodic annual inspection and the random roadside inspection. So my work is to reduce the frequency of this kind of inspection and to introduce the automatic inspection to save time and money for the companies and for the carriers. So I think this is this is worth to do this kind of research to contribute to the companies. Yeah.
Well, thank you. Thank you for being here today and for answering our questions.
Yes, thank you.
You're welcome. Okay, let's go to the next slide, please, Joy. And we're going to be hearing from Grahn in this video, who works with Dr. Chen and Dr. Hendrickson on the optimizing first mile, last mile service performance using transportation network companies.
Hi, my name is Rick, and today I'm going to present my research titled Optimizing First Mile, Last Mile Service Performance Using Transportation Network Companies. And these are results from a Smart Mobility Challenge project with Ride Acta, which is a nonprofit transportation management association that provides on-demand first mile, last mile services to commuters in Robinson Township. My advisors for this project were Dr. Chen and Dr. Chris Hendrickson. The research question for this project was, can we integrate ride-hailing services such as Uber or Lyft with Ride Acta's existing on-demand shuttles to improve performance and reduce costs? We were provided 3 months of detailed ridership data and travel time data in the region. So using this, we developed a model to simulate the system with flexible inputs. The simulation basically worked by assigning each incoming request to a shuttle that produced the smallest marginal costs, or the weighted combination of wait and in-vehicle times for all current and in-queue riders. Optimal routing was then determined by using an insertion heuristic. And if marginal costs were high for a specific request and the ride-hailing fare was low, the request was reassigned to an Uber or Lyft. We selected 3 primary strategies for this analysis, the first being the status quo scenario, which was 2 on-demand shuttles, and this is what's currently in operation now. Second, we created this hybrid system that relied on only 1 shuttle plus ride-hailing services to serve the rest of the trips. And finally, we computed costs and performance metrics, assuming ride-hailing companies serve all requests in the region. So assuming that Uber and Lyft wait times in the region were on average 5 minutes, based on some data released back in 2016, we show that the user costs, which were the weighted wait and in-vehicle times, were quite similar between the hybrid and the status quo scenarios, were within 4%. But from a reliability perspective, the 95th percentile total travel times and wait times were actually improved by up to 30% for the hybrid scenario. So this is due to a combination of very expensive trips being assigned to ride-hailing services and the fact that fewer rides are being shared. We also showed that the costs were able to be reduced by 12.7%, or about $60,000 annually, using this hybrid solution. And finally, we also show that this hybrid system better responds to variations in demand. So when demand dropped to about 50% of normal, we show that the hybrid solution was actually 35% better than the status quo. And these are at their performance in terms of user costs were very similar. So thank you for your time. Please feel free to reach out with any questions. My email is at the bottom of this page.
Okay. Rick, I know you're on here, and we'll have you unmute yourself. And I see Stan's got his hand up. Stan?
Thanks, Lisa Kay, and thanks, Rick. You mentioned the drop in demand in the last slide. Was that due to COVID, and were you looking at COVID data? And just to throw in the broader question that as well, whether or not you were, is there a if there's a change in supply of vehicles, Uber Lyft vehicles, as we saw during COVID, do you think that would have an impact on this type of hybrid scenario? Thank you.
Okay, yeah, great. Thanks for all those questions. So we vary demand to accommodate or to test out situations like COVID. For example, we varied it between 50, 75 to 150% to see sort of how each system responded in terms of, the user costs and the monetary costs at different levels of demand to make it more sort of generalizable and see which one's more robust to these changes in demand. So we didn't look at specific data from COVID because we didn't actually, this was pre-COVID data to summer 2019, but that's definitely one application. And yeah, you're right. During COVID, I think I was reading that some of these costs went up 100%, and there were more surge multipliers because the supply of drivers was down. That's one of the things I discussed further in this research, and why I'm sort of emphasizing that this sort of hybrid solution is actually really nice, because you also have a shuttle. So if you have these surge multipliers coming in and there's an expensive trip, then you shift your ridership to the shuttle that you're paying per hour for the day. And then, maybe during other periods of day when there aren't surge multipliers, maybe you can use some more of these TNC trips because you can gather these prices in real time and make that decision in real time based on the software system that they have. But you're right. The results I'm showing here, you'll likely see higher costs to providing more and more Uber and Lyft rides. But this is a commuter service, and this demand is pretty regular every day at like maybe peak hours. So we would hope that the Uber provider or Lyft provider or TNC provider, I guess, would learn that demand, and then the fares would sort of equilibrate over time at sort of this base fare, because that's essentially what they're trying to do with these surge multipliers. That was a long answer. I'm not sure if it answered all of your questions, but
no, it definitely did, and I do appreciate it's kind of being able to have the advantage of the publicly managed system, but yet also be able to leverage the private system, but not fully rely on the private system always being there at the same price. So I like the hybrid model.
Thanks for your question, Stan.
So one of the other things, Rick, that I'm curious to ask you about is, as you were working on this project, what ended up surprising you the most about the results that were coming out of the research?
Well, I guess the biggest surprise to me was, Uber and Lyft. I've been studying sort of these services for a couple of years now, and they're more expensive than taking a bus from the user perspective, right? You're paying $1.50 to $2.50 per mile on average compared to 25 cents for fixed transit. And so these costs are pretty interesting to me because I wasn't expecting that they would actually be cheaper in many cases. But if you think about, as a provider of these services, you're paying for these shuttles that are, you're paying 8 or 10 hour labor shifts. You can't just hire them for 2 hours during the peak period. And these are fixed costs, and they're more expensive than I think people realize. And I think now, being able to pay on a per trip basis for short trips for some of these types of services is actually comparable or cheaper than hiring out shuttles. And I think we're starting to see that with some of the bigger transit agencies trying sort of these partnerships in their lower density areas, because the costs to them are actually cheaper, even though the cost to you or I would be way more expensive to get an Uber or Lyft. So I guess that was one of the more interesting things that's come out of it. Oh, I think you're muted.
Thank you so much. Thanks for sharing your work. And,
yeah, thank you.
Yeah, we appreciate you being here. Thanks, Rick.
Thank you all.
So our next presentation is going to be from Christoph Mertz, who's going to be talking about his work, Bus on the Edge Applications.
Hello, my name is Christoph Mertz, and I want to talk to you about our project, Bus on the Edge Applications. These days, transit buses often have cameras on the outside to observe their surrounding for security or liability issues. And we want to use those cameras to monitor and assess infrastructure and traffic. So we use a computer on the bus and analyze the video streams. So on the left here, you see how we track people and determine if they're coming in and out of the bus. So we can find out where exactly bus stops are, how many people get in and out at each bus stop. Or in the lower video here, we're counting traffic, and we're counting both parked cars and moving cars. So you can see how bad the traffic is, and also how many parking spots are available. Another application is updating high definition maps. So, and whatever is calculated on the bus itself is then sent to a central location where it might be analyzed further, stored, or acted upon. Here's a concept on how the user might see the system. So there's a map. The light blue is the path of the bus, and then there's some traffic signs it detects. And whenever something happens, it will appear on that map, for example, as a warning. So there might be landslides, or there might be that the sidewalk at a bus stop needs to be cleared. Trash cans need to be emptied, so it detects full trash cans. Or it might notice that there's a new pedestrian crossing and bicycle lane put in at a place. So then it will trigger an alert that the high definition map needs to be updated. So these are all applications we're currently working on. We hope that there will be many more. Whatever the bus company needs or traffic management needs, or anybody who is around the roads, that they can be informed what is going on. So we hope that many more applications will come to that. Thank you very much.
Okay, great. I see Chris Hendrickson, you have your hand up.
Yes, thanks, Christoph. Very interesting. I was curious, how well does your video and software work in nighttime or inclement weather conditions?
So the cameras do have an IR illuminator on it, so we can see at night for short distances, so we can see pedestrians close to the bus. We still haven't looked in detail on how it's going to do in inclement weather. We do have data when it was snowing, so we will look at that in detail. But we'll first do the easier stuff, and then with time we'll look how it is doing in inclement weather. Actually, inclement weather might be very interesting. For example, if you want to see flooding on the road itself, you can only see that when it's really raining very hard, and that doesn't happen very often. So we hope that we will have that kind of data to answer those questions.
Great, thank you.
And Christoph, I know you're working with community partners on this project. I'm curious if they've shared with you some of the applications that they may not have expected to get out of this, that they're actually realizing from the research.
Yes, I mean, it's more like they are surprising me in what they want. So like what you see right here is like the full trash can. That's not something I came up with, but it's a real problem, right? So the bus company, they have to keep the shelters clean, and there's most times there is a trash can, and it's a lot of work to empty them. And you know, how are they going to do that? Are they going to send out somebody on a regular basis, and then maybe sometimes it's empty, sometimes it's not? So it's a lot of work for them, and it would be great for them to know, okay, it's full, so now we need to send somebody out. So this is one of these things where I didn't think at all about that, but they told me that they need it, and it's something which will definitely save them money, and it will make the riding experience better for everybody, because less trash is around.
Yeah, it's a great example of the benefit of having these partnerships with different deployment partners and the people that are on this video with us today, and learning some unexpected things. So thank you so much for being here and sharing your research with us.
Thank you.
And next, we're going to move on to demand learning and supply optimization for last mile transportation in disadvantaged neighborhoods. Peter Zhang and Erin Lin are going to be telling us about that.
Hello, everyone. My name is Erin Lin. Today, I'm going to present our project titled Demand Learning and Supply Optimization for Last Mile Transportation in Disadvantaged Neighborhood. This is a joint work with Professor Peter Zhang at Heinz College. Heritage community transportation offers first/last mile transportation in disadvantaged communities who don't have access to the public transit. There are 3 fixed routes covering the East Pittsburgh regions. The service charges 25 cents a ride and runs on weekdays and Saturdays. There are more than 3,000 riders who are using this service, and 63% of riders' annual household incomes are less than $10,000. The reason that this service is so important to the disadvantaged communities is that the majority of these riders are using the system to connect to the public transit, such as bus. However, after the pandemic outbreak, this transportation service becomes more challenging due to the sharp ridership drop and the increased health risk. As the data shown, the decline rates are over 40% over these 2 years. Additionally, we identified 2 key operational issues faced by HCT: high cost and long rider wait times. From the HCT standpoint, the cost per passenger has almost doubled in under 6 months due to the decrease in rides. And from the passenger standpoint, they will have to wait for 1 hour or 2 if they miss it. There will be 3 phases in our proposed plan. The first is demand learning, where we would design and distribute surveys and analyze the ridership data to understand future demand for this service. Once understanding the various components and patterns of demand, we will move on to the predictive analytics phase, where we would use various machine learning techniques to further understand the potential uncertainty and therefore predict non-stationary trend. The last phase is to provide a service improvement suggestion, such as updating route schedule. In this phase, we would focus on robust optimization to address how a robust solution framework can hedge against uncertainty. Overall, we think this project can bring a strong positive impact, that it would provide us the opportunity to conduct both transportation and social economic research with the goal of serving the most vulnerable populations. Thank you for your listening.
Thank you so much. And this project, I know, is still in progress. Oh, I see Stan has his hand up. Stan?
Thank you. In your process, you have the data gathering, and then the second process is applying the machine learning for the predictive analytics. How do you think that will be different in coming up with new scheduling recommendations from traditional means of coming up with a rescheduling? How is that machine learning going to provide you different results?
Thank you for the question, Stan. This is Peter. So basically, we think of the predictive analytics or machine learning phase as a necessary phase to first understand the underlying data and then also make some projection about what's going to happen in the future in terms of basically the setting, the underlying facts, how people are still requiring this kind of service. And then with that, equipped with that knowledge and information, we can then do better decision making in terms of scheduling, rescheduling, or adding a few stops here and there changing the frequencies or adding a Saturday service or something like that. So these are two parts that are in tandem to each other.
Okay, great. And are you looking at any other data sources outside of just the ridership data, or just you looking at just ridership data?
We have a few three very interesting pieces of data so far. We have ridership data that was we got from 1 year prior to COVID, so March 2019, all the way to pretty much current. So wanted that in order to understand what was the pre-COVID status, and also that gave us a year of pre-COVID information so that we can tease out the seasonality throughout 1 year. And so have pre-COVID and then post-COVID and then until current. And then we also have 3-4 years of survey information about the riders themselves. We added a few survey questions in this year's survey, and we just received them 2 weeks ago. Very interesting results. And then we also have some background information that shows the travel demand in the larger area in Pittsburgh. That came from Port Authority surveys. And there were some interesting demographic information, actual precise demand information as well. And we're looking at we're finding very interesting things. For example, just about an hour ago, Erin and I were looking at the data, and we saw that originally we thought the drop in ridership was because of the capacity limitation during COVID. But now looking at the data, we realize that actually maybe is not the case. And the implication is if the drop in ridership it's actually a demand drop, not a supply cap, then the strategy of how to revitalize demand and how to improve service, that's very different from what we would have done with the previous assumption.
Good. Thank you, Erin. Thank you, Peter.
Thank you.
Yes, thank you. And I love that we're getting results from an hour ago. So thank you so much for sharing those. And we'll look forward to seeing the outcome. Again, another really good example of how this will have a direct impact on the community and on people and their mobility. So thank you for being here today.
Thank you.
Okay, our next speaker, or our next video is going to be on traffic 4D, single view reconstruction of repetitive, boy, they're giving me tongue twisters, activity using longitudinal self-supervision. Woo! This is led by our researcher Srinivasa, Narasimhan, and Robert Tamburo will be on with us as well. And we have some other students who are involved in this too, and they will be introduced in the video. Thank you.
Hi everyone, I'm Dinesh and I'm going to present our work on Traffic 4D, single view reconstruction of repetitious activity using longitudinal self-supervision. This is a joint effort between myself, Dinesh, Robert, Fangyu, Xudong, and Srinivasa. Understanding 4D reconstruction, that is 3D plus over time, is very important in multiple settings. For example, this is useful to compute real-world velocity of vehicles moving in different locations of the city. We can use this for understanding anomalies at intersections. This information can be given as an input to driving assistance systems or autonomous vehicles for better 3D reconstruction. And all of this information across city can be used to monitor traffic as well as give better infrastructure information for city planning. Our input is set of videos which we have captured for long duration of time to understand how to exploit these repetitions happening at different intersections. These repetitions are used as a supervision to improve our 3D reconstruction and detections. Here we show some results in a 5th and Morewood, where we can clearly see the reconstruction of cars on the left and their velocity profiles on the right bottom, and the projections on the right top, where clearly each vehicle is being accurately reconstructed and shown on the Google Maps on the left. Further, this information can be used to detect anomalies. Here we show a wrong turning car, and we are able to automatically detect such cases from all the car motions. Here we show a very close accident, and these kind of anomalies can be automatically detected using our 4D pipeline. Thank you for listening to our talk. For more results and better description, please visit our website. Thank you.
Thank you for the video. And I know when we watch that, I kind of feel like I'm watching a video game with all the different cars moving and going through the streets. And Robert, I know you're here with us today. I think, you know, for those of us who are not as into all of the science and the research part of it, can you tell me what all of that shows us and what does it mean for the average community member?
Sure, I'll do my best. So what you were saying was some algorithms that were developed that do the following. So first, we detect where vehicles are on the road. And then based on those detections, we can identify key points of the vehicle. So we know where the wheel is, we know where the bumper is, etc. And then over time, we track the vehicles to get an estimate of what most vehicles do. So at most intersections, most vehicles behave in the same manner. So based on that tracking information, what you saw is those streaks of colored lines, we can cluster them together to get an idea of what average activity looks like or normal activity. And then as we acquire data and then perform this analysis, we compare it to these trajectories, these average trajectories, to see if there was some anomalous event that occurred. So the magic here is that with a single camera, we can do 4D reconstruction, where normally you need two cameras to do that. And then based on kind of observed average activity, we can determine if there was something that anomalous happened. And to answer, I could follow up with that if that wasn't unclear. And then the second part of your question was, how is that useful to the community? So we thought this would be useful in that activity at intersections or streets in general is kind of like not known very well unless an accident happens and a police report is filed. So we thought that if we could extract higher level information such as near collisions or illegal turns or even, bus stop occupancy or where pedestrians cross intersections, this information would be useful for city planners, for example, to understand the dynamics of the intersection, to see if anything can be done to improve mobility at that intersection. And I'm sure there's other things other than, we're interested in that for the research aspect of it, but in general, it's just understanding activity. We're working with some other communities where they're interested in understanding where pedestrians go. So that's more of kind of following pedestrian activity. So they want to know when someone parks their car, where are they actually going? Are they going to the store? Are they going to the library? And that's towards improving their business district so that they can get some analysis and statistics that show how people travel in their business district. And then there's another deployment where they're interested in also understanding just how pedestrians use the road, because it's an area that has like one major road that goes to their town, and it's connected, houses, apartments, laundromats, etc. And the road does not have like a sidewalk or a shoulder. So they want to understand how pedestrians navigate between their resident and the laundromat, for example, and if they encounter any issues with vehicles during their travels. So kind of getting an idea of pedestrian activity, doing kind of normal daily stuff. And we think, the analytics that we get out of our methods can provide some information that would be useful for their push to get multimodal roads.
Okay, thank you. And I see Stan has a question. We have time for one quick question.
Yeah, just a comment. I think this is very valuable information, particularly the near misses and the origin destination. But can you also do pedestrian and bicycle counts with that? Because oftentimes you know that one pedestrian wants to cross when a signal is hit, but you don't often have data on how many pedestrians are there and waiting, et cetera.
Yeah, counts are no problem. Counts of vehicles, pedestrian, or people in general. So they could be people walking, people on their bicycle, people running, jogging. Another aspect of this is trying to, I think this is further down the road, is to get more statistics on people that have various disabilities. So, identifying people with visual impairments, for example, is another way that we want to extend this. The trick with tracking people or counting people is that, especially in the area of intersections, is occlusion. So when you count a person, you can't count them again to get accurate numbers. So that's a little bit of trick. It's called re-identification. So like if a car passes in front of a person that you already counted, you have to make sure that you don't double count them. So it seems like a simple problem, but it actually becomes quite challenging. But that's definitely something that we can do.
Thank you so much.
Sure.
Okay, we're going to move on to our final project today, which is featuring the future of transit work. We have there's several PIs on this: Sarah Fox, Nick Martinella, Patrick Carrington, Jodi Forlizzi, and Bonnie Fann is here today, and she'll be answering questions afterwards. And the rest of the team is Joselyn Kim, Xander Fann, Meghana, Tara, and Kevin Kim.
Student in the Human Computer Interaction Institute at Carnegie Mellon University. I'm here to talk about the Future of Transit Work project, which is led by co-PIs Sarah Fox, Nick Martelaro, Patrick Carrington, Jodi Forlizzi. And I'm leading a group of students, including Joselyn Kim, Xander Fann, Meghana, Tara, and Kevin Kim. I'm very energized to talk about this project because the conversation around autonomy in transit is a conversation about the future of work, and it is critical to center workers in the future of work. There are a growing number of autonomous vehicle deployments in transit, and it feels very important to understand what the worker impact of those autonomous deployments might be. Also, building off of previous work in HCI, it is clear that without frontline worker input, pragmatic, purposeful, and ethical technology design is not possible. So we want to answer some critical questions in our project, including getting a full understanding of all the core roles and functions of operators, which extend far beyond driving alone, and understanding how those roles and functions will shift as AV applications emerge. We want to further understand how transit workers can be a voice and influence the decision-making around potential AV deployments and rollouts. A few outcomes of this project will include a white paper on potential autonomous technology impact on transit operators' jobs and roles, a strategic roadmap with a set of design proposals for AV tech that center on the future of transit work, and a guidebook for worker-involved collaborative design on transit and autonomous technology. The study will include two major phases. First, using methods of contextual inquiry, and then methods of co-design. We begin with a landscape analysis that provides a technology readiness assessment and case studies of AV transit deployments, basically a where are we now. That will inform two elements of our study, including our diary studies and our interviews, where we get an understanding of the day-to-day experiences of transit operators from our diary studies and conduct a series of interviews across cities amongst multiple operators, understanding their roles, tools, and understandings. That will provide the basis for a deep understanding of transit operation and create the protocols and process for our workshop designs. These workshops will involve multiple members of labor, of operators, technologists, and member of transit advocacy groups in order to collaboratively derive interventions and guidelines around AV in transit.
Okay, well, thank you so much, Bonnie. I'm glad you're here today. I wanted to start with a question for you. As you know, we know the fields and the jobs are evolving. What do you think, you know, in the next 5 years, do you have any thoughts about what things might look like?
That's a great question. I think that doing this study is actually a way to help shape what those next 5 years might look like, just because there are so many worthwhile questions to answer to shape the process of you know, technology implementation and transition, particularly in public transit, where we're considering other things at a sort of broader fleet level, or, you know, service area consideration, where it's not just about the problems of, you know, operating on the road, but it's also about how are we actually serving the public? How are we, you know, meeting the needs of operators? There's definitely within the landscape analysis a lot of movement already in automation in public transit, and it's really clear that things are moving very quickly in terms of seeing new developments even the past month. So.
Okay, thank you. And then my other question, we've been fortunate to work with you for several years when you were a graduate student within the Heinz College and working with us as a Women in Transportation Fellow. And I'm thinking about the students who are watching this webinar and wondering if you have any words of wisdom to share if there are students who are looking to pursue research and wanting to dive more into the transportation topics that you've been able to do.
Yeah, it's actually really great being in this space, seeing so many great researchers and folks that I remember from the mobility seminar series. There's a lot of energy and interest at CMU, despite not having, you know, this maybe a specific transportation studies or urban studies program. And it's clear that actually that can be a benefit in terms of approaching a lot of this work from an interdisciplinary lens, applying sort of, you know, whatever field you're coming from to a lot of emerging problems of transportation mobility, because that seems to be what's really needed to answer a lot of these, you know, emerging questions.
Thank you so much for being here today. And I'd like to thank all of the researchers, students who have been here today to help highlight the different projects that are going on through the Mobility 21 University Transportation Center. I would encourage you to visit our site if you would like more information about what's happening with the research projects themselves.